Hello, I'm Mr. Franklin. Today we're going to be looking at calculating the average atomic mass of a substance. Up until now we've looked at the periodic table, we've looked at the mass on the periodic table, and we've seen that it's a decimal, and we've talked about isotopes like carbon-12, carbon-13, and carbon-14, which when we take the average of the naturally occurring isotopes, that's how we take carbon-12, 13, and 14 and turn it into a 12.011 that we see on our periodic table. So let's look at this. Natural abundance is how often a particular isotope is found in nature. And we use this thing called percent abundance to express this natural abundance. So for example, boron 10. The isotope of boron with a mass of 10 occurs 19.9% of the time. So that's its percent abundance. Boron 11 occurs 80.1% of the time. And what does that mean? That means that if I take a basket and I put boron in it, and I just looked at the boron, if I could count 100 atoms out of that, approximately 19.9, which we can't have a decimal of an atom, okay? That would round to 20. So 20 of those atoms would be boron 10. 80.1, we rounded to 80, would give me 80 atoms of boron 11. Okay, so that's kind of what we're looking at. And if we were to put those together and average them, we would get the mass that's on the periodic table. So let's look at how to do that. Before we do that, though, there's something that we've not talked about, and that is atomic mass units. Normally, we've been talking about mass in terms of grams or kilograms, and we've done our conversions. In our labs, we've used the scale and we measure grams. If we were to measure the mass of a proton, it would be this right here, okay? That's pretty tiny, and we don't like to mess with that. So an atomic mass unit makes the math easy, and what it is a proton has a mass of 1 atomic mass unit, and AMU is the abbreviation. Neutrons have a mass of 1 AMU. Electrons have a mass of 0 AMU. Okay? So basically how many protons and neutrons we have would tell us the AMU. So if we look at boron, 5 and 10.81, how many protons does it have? It has 5. How many neutrons? It has 6, for a total of 11. If we add those together, we get the mass, and that's in AMU, is the unit. Okay? We hadn't really talked about this, so you kind of need to know that before we do this next part. Let's take a look at how this works as a problem. So we have a sample of boron, which has been found to contain 19.9% of an isotope, type 1, which has a mass of 10.012 AMU, and 80.1% of another isotope with this mass. Now, notice that these are decimals, and we're going to need to keep it as decimals for a reason. But it's asking us to calculate the average atomic mass. So here's how we do it. First, we're dealing with boron, so I'm going to write the B, and then write the mass for each one. So I got 10.012, and then I have boron with a mass of 11.009. What's the percentage of each one? The first one has a percentage of 19.9%, and the second one has a percentage of 80.1%. To calculate this, to do this calculation, we're going to multiply those. But if you remember from your math classes, we really don't want to multiply times a percent. We want to convert our percentages to decimals. So when we do that, we divide by 100, and we get 0.199. You know, down here we would get 0.801. Okay, so don't forget, we want to convert it to a decimal before we multiply it. Okay, so now let's look at our calculator. Let's plug this in the calculator. So 10.012 times 0.199 equals 1.992. So let's write that, 1.992. Okay, let's do the next one. we have 11.009 times 0.8, oh, messing up here. 11.009 times 80.1. Now notice this, I did this on purpose. I accidentally multiplied times this. Okay, I accidentally. Because I wanted to show you, this number that you should get should be less than whatever this number is. So see, 1.992 is less than 10, so that's got to be somewhat correct. But look at this number. Way, way too big. So we need to make sure that we multiply times the decimal. So 11.009 times 0.801 equals 8.818. 8.818, which is much closer to 11, and it's smaller, so that's correct. Next thing I'm going to do is I'm going to add these two numbers together. All the numbers here I'm going to add together. So, just got to enter calculator, so plus 1.992, oops, go back 1.992 equals 10.81. 10.81 AMU, atomic mass unit. And if we look on our periodic table, you're going to see that that is the mass that we have on the periodic table. Okay, pretty cool. Let's try another one. This time though, this is something you'll see on your test where you don't know what the element is. So it will say a sample of an unknown element has been found to contain 90.48% of an isotope type 1 with this mass, 0.27% of isotope type 2 with 20.994 AME for a mass, and 9.25% of isotope type 3 with this mass. Calculate the average atomic mass. First thing is, I don't know what the symbol is, so I'm just going to use the symbol X. Okay? And what's the first mass? Let's see. 19.992. And I'm actually going to go ahead and write the percentage here. Be careful, it's not that one, it's this one. Don't mix up your percentages, okay? 90.48%. And then this one is 20.994 times 0.27%. Careful with the percentage. And then we have 21.991 times 9.25%. Okay? So what's the first step? What do we need to do next? Okay? Next we do need to convert these to decimal. So that's 0.9048, 0.0027, 0.0925. 1, 2. Okay? So now we got to multiply. So let's pull out our calculator. 19.92 times 0.9048 equals 18.0236. 0236. Yep. Okay? And then 20.994 times 0.0027 equals 0.0567. 0.0567. Notice I did round there. Okay? And then the last one, 21.991 times 0.0925. 2.034. 2.034. Next I'm going to add. Now, I like to do things in my head, and when I tried this earlier, I didn't line up all my decimals and I added wrong. So I really just suggest that you use a calculator. So 2.034 plus 0.0, 0.0567 equals plus 18.0236 equals 20.11. Okay? And that's in AMU. Let's go back. AMU. Now, here's a question. Can I look this up on the periodic table and tell what element that is? Okay? Now we could argue this. If this is an accurate representation of the masses of an element on the periodic table, we should, because it should match what's on the periodic table, but we can't always rely on the mass to tell us what the element is. What do we have to know in order to make sure we know exactly what element it is? We have to know the atomic number, okay, or the number of protons. Okay? All right. So what you have a paper that's going to have, I think, 4 practice problems that I want you to work through on this. And if you need to go back and rewatch some of that, please do so. And I will see you in class. Thank you.